In the last section of Chapter 1, Section 7, we're going to take a look at quadratic equations now. And this is something you need to be familiar with. This is the standard form of the quadratic equation, where a is the numerical coefficient of x squared, b the numerical coefficient of x, and c is usually a constant, and it equals 0. Now you may recall we had said earlier that if you just take this part, this was the standard form of the quadratic expression. But once you add the equal sign to 0, this became the standard form for the quadratic equation. And these are all examples of quadratic equations. Remember, your degree is to the second power. Now, throughout this lesson, we're going to be looking at a property that's called the zero factor property. And I'll write it up over here. So A times B, each of these would be a factor. And if that is going to equal 0, the only way that can be true is that either A and or B must be a 0. So we often say, well, this is one factor that will equal 0, or the other factor that will equal 0. And that's what we're saying is the zero factor property. Now let's see it in action. Now in example 1, here we have a binomial that we might think of as A, and another binomial that we might think of as B, and then we're saying that equals 0. So this is a factor, and this is a factor, and it equals 0. So the rule, we said that in order for this to be true, this factor may be equal to 0, or this factor may be equal to 0. And this is how we write it. And then we solve. Just transpose the -4 to the other side, and we say x equals 4. Now if x equals 4 here, 4 minus 4 is 0, so that would be true. And then here we transpose the 7 to the other side. It becomes a -7, and then we divide by 3. And if we put that into this, this will become a -7 here eventually, plus 7 is 0. So it checks. Now you'll be doing practice in QuizMes, but looking at these checkpoint over here, notice these are factor, factor equals 0, factor, factor equals 0. In this case we have 3 sets of factors, and we equal them all to 0. And that's how you would find solutions for this here. Now, we use a lot of zeros in this formula, and sometimes in algebra you might come across the statement, finding the zeros. Finding the zeros, that is, what would make each of these factors a 0? And that'll be something we look at a little later in this section. So looking at example 2 now, we see a quadratic equation here. I just copied it here. And you might say, is this in standard form? And the answer is no. In order to put it in standard form, I have to take the 3 from this side, move it over, and on this side it becomes a -3. Now it's in standard form. Now, we're equaling it to 0, but to use the zero factor property, we have to factor this trinomial, and let's see what we get. Well, they've done it for us here, so let's just use that. 3r and a 2r, and to get a 7, I'm going to have to use the 3 there and the 1 there, and they're all going to be positive. So we could spend time factoring, but it'll just take a lot of time, and we'll assume that you're able to factor it. Now, what do you do next? Well, you rewrite it as we say. This is going to be our protocol. And I think I factored it in. And I was foiling that mentally, and that didn't work. So again, we have to have the proper factorization. You'll have to spend time ensuring that when you get your examples. But now we get a 9 minus 2 is a positive 7. So this checks out. So here we are then putting each of our factors equal to 0. And this is the protocol. This is the work we'd like to see on your blue sheet. Now you solve, transpose the 1, negative 1. On this side it becomes a positive 1. And then you divide by 3. And here you're going to transpose the positive 3 to this side. That becomes a negative 3. And then divide by 2. Okay, now we're in business. Now every once in a while I've seen also that they say these are the answers. What was the original equation? Or what was an equation for this? Well, you just reverse all these steps. FOIL this, you get this. Now you may not know that you had to take that negative 3 over to the other side to get the real original equation, but this one would be close enough. Again, they're not asking for that here. Here they're asking to solve this quadratic equation, and we're using the technique of, once we put it in standard form, to factor it. Take each of the factors, equal it to 0. And that's that old principle AB equals 0. Now, another property that we're featuring here as we go into example 3 is what we call the square root property. And if we have something like this, m squared equals 17. Now, when we have something like this, to solve for m, we just take the square root of this side, and that will give us an m. But to ensure that we get two answers, we have to go plus or minus the square root of 17 on the other side. And that is our solution. So this was a super easy one when you see it in this form. Because if you did it the other way, m squared minus 17 equals 0. This doesn't factor. So we couldn't use the difference of perfect squares. But notice if this were a 16 here, this would factor into m plus 4, m minus 4. And we would get two answers. M is a negative 4, m is a positive 4. Now, remember, if we use this technique, let me clear this for a moment. If this were m squared equals 16, and we factored that, once we put the 16 on that side, we would get two solutions. That's why we need the plus or minus here. that ensures we get both solutions. Now, a variation of this is when we have something like this. Y minus 4, the quantity squared, equals 11, which is example B. Now, can we take the square root of this? Absolutely. But when we take the square root of this other side, it's plus or minus the square root of 11. So we get y minus 4. Remember, when we take the square root of something that's squared, we just get the radicand. And then this is plus or minus the square root of 11. And how do we isolate the y? Well, we transpose the negative 4 to this side as a positive 4. And here we have an irrational solution, because square root of 11 is irrational. And they're showing all of this there as well. Now, using this technique up here to develop something like this, we can actually take the quadratic formula, or I should say the standard form of the quadratic equation, and solve for the letter x. When we do so, we get this, which is the quadratic formula. Now, key to this, when we look at it, is we have to identify what our A term is, what our B term is, and what our C term is when it's in standard form, because that's how this formula was derived. Now, I do a solution of this, and there should be a link right up there for it. So in example 4, they're asking us to solve this by putting the values into the quadratic formula. But this is not in standard form. So the first thing we do is transpose the 4x to the other side and put it in standard form. Now, once it's in standard form, we can identify our A value, which will be a 1, our B value, which will be a negative 4, and our C value, which is a positive 1, and that's what they're suggesting. We then carefully take these values and substitute it into the quadratic formula. So this was negative b. Now the negative is in the formula, but b itself is negative. So we initially put it this way and use the technique of the opposite of a negative is a positive. So it goes into our formula as a positive 4. Now this is b squared that we're going to square, becomes a positive 16, and then negative 4 times a, which is 1, times c, which is 1, all over 2a, which is 2 times 1. And we get this. Now, when we do the subtraction here under the radical sign, we get a 12. And we know the square root of 12 is actually the square root of 4 times the square root of 3. And the square root of 4 is 2. And then we have the square root of 3. And we get this. But now notice we can factor out a 2 from each of these terms. And then now all of this is over 2. And we see we can cancel here. And this is what our answer is. Now you're going to have a couple to do like this. The strategy is put it in standard form. Identify your A, B, and C. Substitute carefully. Start simplifying. And then you end up with your answer. Now theoretically, this is a good answer as well. But simplified, this is the answer. Now the book is also saying, because of the plus or minus sign in front of the radical, we're going to get two answers. A plus square root of 3 here, and a minus square root of 3. And if you wanted to convert this using your calculator, you do get values. And of course, where these are exact answers, these are approximation because of the irrational nature of the square root of 3. Okay, let's go on to example 5, where we're going to read it over and see what we can come up with. So here, this company's profit followed a pattern that can be expressed by this quadratic equation here. And there's x squared x, and there's our constant. Now, they're saying this x value is between a 6 and a 12, and it's going to correspond to the year 2006, where net earnings were this much. So we're going to put this much for E over here. We're then going to transpose this to there, subtracting this from that, and now we get this. So in applying the quadratic formula, they're doing the radical part first. And of course you need a calculator for this. The numbers are enormous here. But this is your A, this is your B, and this is your C. And that's what they've done. They've substituted. So under the radical, you end up with this. Now that we have a value under our radical sign, we can continue putting that into the rest of the formula, and when we do so, we end up with approximately 12, and here approximately 7. And they're saying, since we were told that the net earnings had recovered, we use a solution later in time, and that x in this case would apply to the year 2012. And that's the answer they're looking for. Again, this looks very tedious, and one little mistype can mess up your answer. So you have to take this slowly and carefully. All right, let's go on to 6. And initially you'd have to have the quadratic formula handy, but it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And if you write that a number of times, hopefully you'll remember it. And then again, this is in standard form, so you're carefully defining what a is, b, and your c term, and then substituting, and eventually you get this. Now, since what you have under the radical sign ends up being a 0, you only get one answer. But theoretically you're getting 2, but they're both the same. So we think of it as one answer. Now in example 7, again, using the quadratic formula, you have a 1 there for your A, a negative 6 for the B, and a positive 10 for the C that you carefully substitute. And you see now that under the radical sign, you end up with a negative. Now, this is not going to be a real number because there is no real number solution for the square root of a negative 4. Later we might look into this, but this is an imaginary number, so it's not a real number. So when you end up under the radical sign with a negative, this is not a real number solution. Now this is a solution, it's just not a real number. So, since no negative number has a square root in a real number system, the square root of negative 4 is not a real number. Hence, the equation has no real solution. Now, whether or not we get a real solution or not depends on what is under the radical sign. And this leads us to our next topic, which is called the discriminant. And what is the discriminant? It is what is under the radical sign, which is b squared minus 4ac. This is the discriminant. Now, if this is greater, as they're showing you, greater than 0, if your discriminant is greater than 0, you're going to have two real number solutions. If it equals 0, you're just going to have one solution as we had above. And if it's less than 0, they're going to be negative, and there are no real solutions. And that discriminant tells you that. And here is the summation of it. Going on now, we're going to take a quick review of the Pythagorean Theorem. And for this, we have a little picture of a triangle. Triangle has three sides. Here we see a shorter side that's often referred to as a leg of our triangle. The longer side is another leg. And then between the legs, there's a right angle, 90 degrees. And the side opposite the right angle is called the hypotenuse. And the rule is, if we take this first side and square it, and take this second side and square it, and add these together, it will equal the square of the hypotenuse. Such as if this were 3, and this were 4, and this were 5. 3 squared is 9, 4 squared is 16, and 5 squared is 25. And notice that 9 plus 16 is 25. 25 equals 25. So the Pythagorean theorem states the sum of the squares of the legs equal the square of the hypotenuse. Okay, well, that's an easy just a statement of what the Pythagorean theorem is. Now what we have to do is just check out example 8 here. The size of a flat screen television is the diagonal measurement of its screen. The height of the screen is approximately 63% of the width. So as we mentioned before, you make a little rectangle, and this will be the length, and the width is 63% of the length. Kathy claims that John's 39-inch flat screen has only half of the viewing area that her 46-inch flat screen television has. Is Kathy right? Well, to figure this out, we have to use the Pythagorean theorem to find what is this x value over here. What is the length, and then what is the diagonal of the screen, and compare them. Okay, so here, once we put that into the Pythagorean theorem, we're going to have x squared. We're going to have this squared, and we know that 46, we're going to square that. So the square of this plus this, the square of that, equals the square of that. And I have it worked out here, so we can follow along. This squared, this squared, this squared. Now, we're going to factor out an x squared there, or in a sense there's a 1 there. We're just going to add these together. And now we're going to divide both sides by this. We get that, and then we take the square root of both sides, and we get that. And then again, of course, we're using our calculator. We're going to get this. So notice that there's a negative as part of our answer, but we just reject that because we're not interested in that value. So this side here is 38.9. So then we take 63% of this, and we get our width. And as they're showing, length times width gives us 953.1 square inches. And again, we're wondering, is Kathy right or not? So we have to keep that in mind because we're going to move on to the next section. So as the text is describing, we're going to take the other TV set now, which has a diagonal of 39 inches. And we've just changed the letters here a little bit so we can run that. And then following exactly the same procedure, we get our base is 33 inches. We reject the negative. We're not going to use that. And then 63% of the 33 gives us this. So when we multiply the two together, we see that this square inches compared to the other is much less, since half of this is this. Kathy is wrong, because John's viewing area is this many square inches. So going back to the original screen here, it says that she claims that this screen is only half the viewing area. Is she right? And she is wrong. It's a little more than half, but it is a smaller viewing area. Anyway, lots of stuff to do to get to an answer. Now, as we look at example 9, here a landscape architect wants to make an exposed gravel border of uniform width around a small shed behind a company plant. The shed is 10 by 6 feet. He has enough gravel to cover 36 square feet. How wide should the border be? Okay, now here's a case where a diagram is absolutely important, and there is one here. So let's look at this. So as you do your work, you're going to need to make a diagram. You get one like this. So there's your shed, 10 by 6 feet. and you're going to have a border around it. Now, how much will this border be in terms of length or width? And again, we don't know. Well, that's the beauty of algebra. It's going to be x. So for our width here, it's going to be 6 feet plus how many x's? Well, there's 1x here and 1x there. So 2x. Now, how about this length? Well, we know it's going to be 10 feet plus, again, an x on this side, an x on this side. Now, we want to find the area of this blue area here. So we can subtract out this area that we know is 6 times 10, which is 60. And that's going to equal the amount of gravel, which we know is 36 square feet. So there's our formula. Now you might say, oh, it's in factored form. Well, not so easy, because you have to put it in standard form. This is not standard form. So the first thing we have to do is FOIL this, transpose this 36 to the other side, where this will become a negative 96. And I see they are integrating this a little bit here, so let's not do it that way. Let's just FOIL this first. So they FOIL this over here, and they get this. Then they have a 60 and a negative 60. That's where these just cancel out. Okay. Now they transpose that. So then we get x squared plus 8x minus 9 equals 0. Now, interestingly, this factors nicely. So that's another tool in our toolbox. We need a positive in the middle, so this will be a positive, and this will be a negative. Now again, we're going to equate each of these factors to 0. This is my little shortcut. So here x equals 1, or x equals a negative 9. Now here we're getting two answers, because this is a quadratic equation. But can a border ever be a negative number? No. So we reject that answer. And what is the dimensions of our border? 1 foot around will make this an area around of 36 square feet. And there we see the work and the solution. All right, going on to another aspect of using the quadratic formula. In physical science, if an object is thrown upward, dropped, or thrown downward, and travels in a straight line, subject only to gravity with wind resistance ignored, the height h of the object above the ground in feet after t seconds is given by this formula. Okay. Now, to apply this formula, we need to have some background as to what these letters refer to. And it's given h sub o is the height of the object when t equals 0, that is, time is starting, and v sub o is the initial velocity at the time of starting at 0. The value of v sub o is taken to be positive if the object moves upward, and negative if it moves downward. Now, suppose that a golf ball is thrown downward from the top of a 625-foot high building with the initial velocity of 65 feet per second. How long does it take to reach the ground? Well, your h here is going to be a 0. That's the ground. And there's the formula for time so far. And you're starting off, your initial velocity time when you're starting off is going to be 65 feet, and it's being thrown downwards, so that's negative 65. And the height of the tower you're throwing it from is 625. So again, when you have one like this, you're going to need to spend time reading it over and figuring out where things go. But once it's in now standard form, you have your A value, your B value, and your C value that you put into your formula, quadratic formula, ending up with this. And then when you end up with, you get a negative value or a positive value because of the plus or minus here. Now, is it going to take time to throw something down? Yes. So you reject the negative value, and this is your answer. And we'll see it in just a moment here as I raise this up, and there is what you'll see. Now again, if you're off just a little bit, MathLab may be critical, and so be careful and don't round off or do anything until just the last stage of it. Now for our last exercise, 11 here, we're asked to solve for the letter x. And here's our formula. V equals mx squared plus x. And you might say, well, we could use what method? Because we have an x squared. Well, the key to this is a quadratic equation. So if we put this into standard form, mx squared plus x, bring our v over as a negative v now, we have this equation in standard form. So can we solve for x? And the answer is yes, we can use the quadratic formula. But again, we have to identify our a value, which is m, our b value, which will be a positive 1, and our c value, which is a negative v. So notice they did the substitution here very carefully and have solved for x. And notice we have a negative and a negative, which made this a positive, and that is our answer. Okay, well, you're going to have plenty of examples to do and to hone your skills, and hopefully can memorize the quadratic formula. Lots of things in this section.